Okay, now let's continue on with our lesson of writing linear functions from a word problem. And we are going to decide if we're going to write it in slope-intercept form, point, slope, or standard form. It just depends on what data is given to us. Katie's candle was 10 inches after burning for 8 minutes. Each minute, the candle burns 1/4 of an inch. Write and graph the function to represent the height of her candle. So we do have a constant rate of change. It says each minute the candle burns 1/4 of an inch. So burning indicates going down. So our M value is going to be -1/4. Each minute it goes down. So our input value is going to be minutes. Now we do not know the initial height of the candle, but we do have a data point that in 8 minutes, the candle is 10 inches. So this is a data point. So I'm going to just write our data point right here. Now we have to decide, is 8 the x coordinate or is 10 the x coordinate? So if we talk about minutes and inches and this candle is burning, the independent value is going to be minutes. The dependent value, the total height, is going to depend on how many minutes the candle's been burning. And typically in word problems, not always, but typically time is usually the independent value because time is always passing by. So in 8 minutes, the candle is 10 inches. So that's a data point. And we know our constant rate of change is -1/4. So in 8 minutes, so our x is going to be minutes. Our y is going to be the total height at a particular moment in time. So we have a point and we know the slope. So we're going to use point slope. So I'm going to use the version where the y1 has already been brought across the equal sign. So y equals my constant rate of change times x minus x1, which is 8, plus y1, that is 10. We could go ahead and plot the point 8, 10. So these are going up by 5s. And these are going up by 1.5s. So 3, 6, 9, 12, 15. So this would be 1.5. So we could say at 0 minutes, oh, we don't know that yet, excuse me. At 8 minutes, the candle is about 10 inches. So we'll put about right there. Okay, let's go ahead and convert this to slope-intercept to see the initial value or the initial height of the candle. So we're going to distribute the -1/4, bring down the plus 10, and now we have y equals -1/4 x plus 12. So we can see that our initial height in 0 minutes of burning, the candle is 12 inches tall. So I think it would be a good idea, since we know we have a negative rate of change, we will have an x-intercept. So let's find how many how many minutes, x, is it going to take for the candle to be 0 inches. So I'm going to plug in 0 for y. This is your x-intercept. So we're going to subtract 12 from both sides. That gives us -12. But don't worry, we have a negative value that we will be multiplying by. So a negative times a negative is going to give us a positive answer. So now we're going to multiply both sides by the reciprocal of -1/4, which is -4. So x, the x-intercept, the number of minutes it's going to take the candle to burn out is going to be -4 times -12, which is +48. So 0, 48 comma 0 is right here. So we have 3 points. We have the y-intercept at 0 minutes, the candle is 12 inches. And in 48 minutes, the candle is 0 inches. And then the data point of 8 minutes, it's 10 inches. So let's go ahead and do our domain. Our domain is minutes. So we already know that the candle can burn from 0 minutes all the way to 48. We don't even need to plug these X values in to get our range because we can use our graph. So we know that the candle can be 0 height, and then we know the maximum height is 12. So the height of the candle is our range. So from 0 to 12 inches. Okay, now we have to decide, can we connect the points or do we need to plot them and it be a discrete graph? Can we have partial minutes? Well, absolutely. We could see at any moment, like in 2.2 minutes. Can the candle be partial height? Can we go in between inches? Absolutely. So this is going to be a continuous graph. That's not totally straight, but you get the point. So I can just connect my X and Y intercepts, and this represents the height of the candle at any given minute between 0 and 48. So I'm limited to my minutes, and I'm limited to the height of our candle. It says how many inches is the candle after burning 12 minutes? So we can plug in 12 into our function. Let's see, y equals negative 1/4, plug in 12, and then plus the 12 of the initial value. So y equals negative 1/4 times 12 is negative 3 plus 12. The total height in 12 minutes is going to be 9 inches. So we could see in 12 minutes, that's about right here, it should be on the 9, and that is exactly right. Okay, so that was using point slope. The Kinsey Tree Farm plants Douglas fir trees. Each year they grow 1.5 feet. So each year they grow 1.5 feet. So that looks like a constant rate of change. In 4 years, they are 8 feet tall. At 16 feet, the farm cuts them down for Christmas trees. So we do not know the initial height of the trees when they're planted, but we do have a data point of in 4 years, again, we have time, and usually time is our input values. In 4 years, the trees are 8 feet tall. So in 4 years, so the X is years, and our Y coordinate 8 is time, so total height, not time. Okay, let me say that again. X values is years, and the Y value is the total height of the tree at a particular year. We also know that they grow 1.5 feet each year. So this is going to be our slope, our constant rate of change. So we're going to use point slope. We have a point, a data point that's not the initial value, and we have the slope. So they're going to grow 1.5, and then we have X minus our X1 value plus our Y1 value of 8. And again, we could plot this, but let's just go ahead and convert this to slope-intercept form. We're going to distribute the 1.5 and then combine the two constants. And the initial height is going to be 2 feet. So these are going up by 3s. And these are going up by 1. So at year 0, when they are planted, they are 2 feet tall. So that's about right here. And then it says, we have to look back at the situation. We are restricted with height this time. So it's 16, this is about 16, we'll say. At 16 feet, the trees are cut for Christmas trees. So do we know our domain? Well, we do know the least amount of years is 0. We don't know how many years it's going to be for the trees to reach 16 feet. We'll find that in just a minute. We do know the least height. So remember, our range or our Y values, this situation is height. They are 2 feet, and then they grow until they're 16 feet. So we can plug in 16 for Y to determine the greatest amount of years. So at 16 feet total height, how many years, X, is it going to take to reach their full height before they are cut down? So we are going to subtract out. We're going to subtract out 2, and we're going to get 14. And then when we divide by X, we get 9 and 1/3. So 9 and 1/3, and that's okay that it's a rational number, is the greatest amount of years that the trees will grow. And 1/3 of a year is 4 months. So we could say 9 years and 4 months is our maximum amount of time that the trees will grow. So how long will it take the tree to reach its maximum height? We just said 9 and 1/3 years. Okay, now let's plot some points and decide if we can connect them. So if we plug in 2, 1.5 times 2, that's 3. 3 plus 2 is 5. And let's go ahead and plot our greatest amount. So we said 9 and 1/3. So 1/2 is 9.5 is right in between. 1/3 is just a little over. So 9 and 1/3 years, it's going to be right here, about right there. Now, can we have partial years? Well, absolutely. And can we have partial height? Of course. So this is going to be a continuous graph. And so we are going to connect the points. So again, we used